4th of July, almost era coming up to you. It is I, Aaron Freeman.
4th of July Eve.
4th of July Eve. 4th of July Eve. I'm Aaron Freeman. My good buddy here is Nicholas Gross, lecturer in physics at Boston University. And because it is the 4th of July and we are all going to be watching fireworks, we're going to talk about
things that go boom in the night.
Well, because we're talking about this because there are lots of interesting things that go boom and explode and protrude in the sky, not least being, say, the sun. But
oh yeah, right.
But
yeah.
You start off. I mean,
and it's got different kinds of booms that it does. but yeah. So we were talking about. I mean, one of the things that I'm always like when I'm watching fireworks, I'm always interested in the different ways of that they're propelled into the sky, right? So there are mortars and there are so when they're propelled into the sky, there are mortars and there are rockets, right? So the mortars, the charge, you could make this. Well, okay, make this home. I don't want to tell people, but you get a piece of plastic tubing, right, and you have to put a charge underneath then the thing that's going to explode. So first you've got the charge that launches it into the air. Right. And that's an explosion that happens quickly, right? I mean, relatively speaking, it's got to happen, won't say instantaneously, but all the energy in the charge that launches the then shell, that they call it a shell, into the air, that then contains all of the fireworks, right? The stuff that will burn and light up the sky, and launch it into the air. But then you can also have a rocket that burns, relatively speaking, more slowly, and ejects the gas that then launches the thing, and that's going to have a different trajectory.
And it's a different bunch of equations that will describe its motion, its movement. That the simple, like with a mortar, it's simple ballistics. That from the moment the motor leaves, the only force acting on it is gravity.
Right. It gets launched, it gets an initial acceleration. So when it's in the tube, it gets some acceleration, but then once it leaves the tube, there's no more acceleration. It's only gravity that's accelerating it.
As opposed to rockets.
As opposed to rockets, which will have a different trajectory, and because there's a constant force being exerted on it as long as the propellant is involved. And when I was a kid, I mean, I turned into a physicist, and most physicists did something like this. I played with making my own gunpowder, and you can get, and I should have looked it up, saltpeter, which I think is nitrogen, right, and then charcoal and sulfur, right, and so those are the funky thing is that depending on the type of explosion you want or type of burning you want, I mean that's really what an explosion is, right? It's burning.
Really fast burning.
Although it's all self-contained burning, it doesn't require oxygen. Right. That's the interesting thing. Is the oxidizer is in the stuff.
You mean in rockets?
In rockets and in gunpowder.
Oh yes. Okay.
It doesn't. So I'm almost. I haven't checked this. I'm almost positive, but
that is my understanding as well. But
so
what that's worth.
Right. So the gunpowder, so you can put the gunpowder in a vacuum and it'll go off, right?
I was saying that in a sense, the motion, the universe is ballistic to the extent that there's no, to the extent that it is all the coast phase after the Big Bang.
Mm-hmm.
That's stretching. It's stretching. But what I'm saying is there was this, like you say with the mortar, there was this big single explosion, and everything, and after that, it's gravity working on everything, keeping it, or dark energy, pushing it back together. But it can be described, but for the dark energy, you could describe the motions just as an.
Right, and I was going to So I would in the old standard model, right? Which is I mean, I know you're a big fan of the standard model. You've been hanging around.
Absolutely.
Get you away from these particle physicists.
I was in Chicago at Fermilab. The Fermilab is like the Cubs. You just gotta love it if you live in Chicago. and Argonne is like the White Sox. The other.
Yeah. Okay.
Anyway, but yes, you were saying. Go ahead. I'm sorry. I love you so much.
So yeah. So it. I mean, I think you hit on the fly in the ointment of your theory of your hypothesis, right? Yes. So it's initially we would have thought that there was some release of energy and the universe was expanding. And the only thing that was working on it was gravity. I would say the fly in the ointment is the dark matter and dark forces associated with that. And I don't know how inflation.
Right. Yeah, because
I don't, and I'm outside expertise, so I'm not. But there's this whole inflationary period where there was something else was pushing things apart faster. That I don't fully get. So, but it's not a bad. I don't think that's a bad vision for people to have. Is that where we've been thrown apart? And this is the idea of that four-dimensional space. All of the galaxies are moving away from each other at the same time. Because the space is expanding.
And of course, the reason that that we hypothesize that dark matter is that the way it should be moving much faster, and it should be soup by now. And the fact that the universe is not soup, and it's sort of like, isn't this our boy? It's sort of like our cosmological constant. That Einstein said was the greatest mistake.
Yeah, it comes back into vogue every 20 years. There's fads in physics as well as fads in fashion.
So one of the
if you stick with an idea for long enough, it'll come back.
It comes back. That's right. I understand. It's like double-breasted suits, although wingtip shoes never do. So one of the things that we see when we see fireworks shooting up, one of those mortars that'll shoot up into the air and then explode, it describes an arc. And that arc is the function of gravity. But when we look at the sun, we see solar flares describe an arc, but yes, it is. When we see solar flares, it's describing an arc because the gravity of the sun.
You're gonna commit to this, aren't
you? Well, I'll commit to it long enough for you to tell me I'm wrong. But I'm gonna tell you.
There's this interesting balance on the surface of the sun, and a lot of the arcs you see are due to magnetic forces and magnetic interactions. And so the sun's magnetic field, in fact, I'm just working on something about this right now, but the sun's magnetic field is incredibly strong right near the surface. It obviously, as you get further away, it gets weaker, but right near the surface, it's very strong, and has to do with our it has to do with the currents that are being generated below the surface of the sun because of the motion of the plasma inside the sun. But so some of those arcs that you see are actually the plasma sitting on the magnetic field. And so there's lots.
Wait. Say that again. So the arcs, some of the arcs that we see described in photographs of solar flares are what?
They're the plasma.
The plasma of the solar surface, the kind of watery sort of.
Well, at the solar surface, it's got the density of water. beyond the solar surface, there's an atmosphere, there's a solar atmosphere
visible during the total eclipse.
Visible during a total eclipse, also visible to instruments in space if they do the thing where they block out the sun and then you can see around the sun. And their density changes, but you can think of it as the atmosphere, right? And so it's much less dense. And so the magnetic structures then are very important in that.
And so when we see those flares, we're seeing plasma riding on a magnetic wave. Oh, that's so.
Magnetic changes in magnetic topology and.
Now we all know that tomorrow, tonight, when we're watching those fireworks, we know that the light that we see is light that was produced virtually instants earlier. We know that I thought I knew that when I was watching sunlight, I was looking at what light that came up with how the sun looked 8 minutes ago. But you told me that.
Well, so that light, and certainly it left the surface of the sun 8 minutes ago. Right. But if you were to try and trace back the path that it took, because it's being generated in the interior, and it can take tens of thousands of years for it to find its way from the interior of the sun, bouncing around in the plasma, maybe getting absorbed and re-emitted as different light and interacting with the plasma, and then finally reaching the surface and being emitted.
So you're saying that the photons that are hitting my face now or hitting up through my window could have been created initially long before my grandparents were born.
Yes, right. In the interior of the sun, where that's generated. So
that is so amazing and weird. That's something I completely, utterly did not know, and this is why we hang out with you physicist people, because you tell us really bizarre and strange things. So there are, and of course, the explosions that we see on July 4th are minor compared to some of the other explosions that we see on the planet, not least being volcanoes.
Sure.
That go, as a matter of fact, I
wouldn't hold one in my hand.
Well, no. Yes, I mean, I understand. We're just talking things that go boom in the night. As a matter of fact, I have a T-shirt. Do you remember that volcano that went off in Iceland about a decade ago, and it ruined air travel in Europe?
Yeah,
Do you remember the name of it?
No, because nobody could pronounce it, or people spent weeks trying to pronounce that name. So
we were in Iceland anyway, but it's just excellent. Thank you. But we're talking about
you're a better man than I, Aaron.
Well, I spent enough time in Iceland, and I asked enough people the exact same question. Oh, hello, Sasha. So. But we were talking about fireworks and things that go boom in the sky with Nick Gross, physicist and lecturer at Boston University. Now, we see a few folks that are there. Uncle Wilton. Now, Wilton is a good buddy of ours who actually taught science, among other subjects, himself as a teacher. And he's a teacher and a very generally curious kind of guy. What makes things glow? And glow. What makes things glow? Glow. What makes in a physical sense? What makes things glow?
So I think there's a couple of different things you got to think about, and so there's two basic mechanisms for emitting light. One is things emit light because they're hot. Okay, and that's so-called thermal. Well, I refer to it as thermal radiation. Classically, in physics, it's referred to as black body radiation.
Black body radiation. And classically in physics, things that glow are considered black.
And yes, well, they're considered black bodies because So I mean, your personality is a fine example of this, Aaron. You glow. And part of it, and actually you're a good example of this, part of it is because you both absorb and emit in the same proportion. So you absorb, so if I think so, and what I'm thinking of is your personality both absorbs and emits, right? And so black bodies are these quote unquote black body emitters are both perfect absorbers, but they're also perfect emitters. So they will emit at the temperature. So if you put a black body in an oven kiln and turn on the oven kiln at 700 degrees, and you see the walls of the oven are both emitting and absorbing the light.
Okay.
Simultaneously, right?
So
and you get this glow that's going on. Right.
So so are the fireworks that we'll see tomorrow and tonight, are those black body? Is that light?
I would say that those are not black bodies typically, in fact, because you would think they were because they're burning and they're emitting light, but it's not just because they're hot, but you get those are more emitted because of atomic spectra interactions. So different elements have different proportions of colors that they put out, and they put out colors in very specific spectra. So this is more like the so-called flame test.
Right.
So I don't know, right? So you take sodium and you put it in, usually you use like methane because methane burns in a sort of pure flame. You take sodium and you put it in there and it burns yellow. Right. You take copper and it burns green, right? And those are characteristic of the elements that you're using. So for a black body emission, it doesn't, the material that the black body is made out of doesn't matter. So the sun, interestingly enough, so when I think of black bodies, I think of irons coming out of a fire. I think of an oven kiln, looking inside an oven kiln. Think of a stove element, heating up a stove element.
So now, how are we describing the light that we will see on our little 4th of July fireworks? It's not black body, thank goodness. I would say that's more about the spectral emissions. Spectral emission. I like spectral emission. I like spectra these days. I'm way into spectra. All right, so we will see spectral emissions of light. Emissions of spectral light.
Yes, right. And so because you're seeing the qualities of the material that's burning and the spectral qualities of that material.
And the arcs that the mortar, the ballistic arcs described by those mortars being shot up to the sky to explode, that we were watching gravity affecting a flying body, or gravity, a projected body, much of gravity affecting a projectile.
Yes.
All right, that's cool. That's cool. And of course, we're seeing light as it was just seconds. The seconds or instants, less than seconds.
Well, yeah, nanoseconds, I would say. I mean, something like that. So 1/10 millionth of a second or something. I mean,
out there in the bright sunlight, we may be absorbing photons that were created in the center of the sun maybe tens of thousands of years ago. Now there's something I'm really going to be. I'm not only pleased to take that into my 4th of July parade. I'm delighted to know it now. I'm delighted to think now. I'm looking at old photons bouncing off my tree.
Look at those old photons. They're tired. They're worn out.
Well, I know you got
feel pretty hot out.
Well, my dear, and very, very entertaining friend, Nick Gross, Dr. Nick Gross, lecturer in physics at Boston University, my pal. We're here as often as we can, trying on Tuesdays usually, to talk about physics. And thank you so much for enlivening and deepening my appreciation of the 4th of July with your physical knowledge.
Well, thank you. It's always a pleasure to talk to you, Aaron. I love our conversation.
So do I, my dear brother. Have a great 4th of July and look forward to talking to you next week.
All right, you too.
Be well, brother. Bye-bye.